Hello, my name is Drew Rasmussen, and today I will be talking about how plastic bags are made, specifically the brand Ziploc. But this is not limited just to Ziploc bags, as many of the generic brands are going to use the same manufacturing process. This is all part of my MSE 215 materials processing project. Let's begin. So, these bags are going to have a few desired specifications. Um, that need to be met in order for the consumer to purchase them cheaply and recycle them, as well as the manufacturer to produce them for a cheap price that's going to in turn allow the consumer to buy them at a relatively low cost. Bags are going to need to be lightweight. This will help with the shipment and the distribution of the bags, as well as the manufacturing. You don't want these things to become too bulky when you're trying to produce them. Larger machines are going to cause or be needed, and this is going to drive the price up. Bags are going to need to be cheap. This is for both the consumer and the manufacturer. It will help if they're highly recyclable, as in a large portion of the material used for these bags can be recovered to be reused to produce bags. They're going to need, which in turn, reusable. Kind of the three R's: reduce, reuse, and recycle. So if they are reusable, then we can eliminate the recyclable process and we can reuse them a few times before having to go to that, saving the consumer money. They need to be compact. Again, this is going to help with distribution. As well as manufacturing. They need to provide protection of contents from the surroundings. Here, this is talking about if you have a dry product inside of your bag, you don't want it to become waterlogged, or you don't want something that is volatile in oxygen to become oxidized. Then you are also going to want a low amount of energy required to manufacture these to keep the cost of manufacturing down. So what is it? What are plastic bags made of? Plastic bags are made out of polyethylene, which polyethylene is a polymer consisting of ethylene units, which if you look at the middle of this slide, we have two carbons, each with two hydrogens attached. This satisfies the four valence electrons of carbon. Now, if you look at these parentheses, you're going to see that there's an N subscript. This N denotes a repeating unit of this ethylene monomer, which is inside the parentheses. So when you think of polyethylene, what you're going to have is chains of these ethylene units, and these can go from tens to thousands of monomers in length. The different types of polyethylene, such as linear and low density polyethylene, refer to how the polymer is formed. For example, linear polyethylene is going to be short chains of polyethylene. And again, these are going to have different characteristics from one variation to the next. In polyethylene bags, however, they use a combination of linear and low density polyethylene um, to melt down and produce the bags. Polyethylene's low melting point allows large chains to be formed, therefore, it is a thermoplastic polymer, as discussed in Chapter 8 of the textbook. So, this slide shows the polymer beads. These are little polyethylene beads that were actually used in the video that I posted on my Digication. These are what are melted down after being mixed together to form a homogeneous solution. This is just kind of the basic. This is where all the bags begin. They are melted here into a vat of liquid, which can then be elongated to form what we know as bags. The steps of manufacturing. So polyethylene is mixed into a homogeneous material, as discussed earlier. These granules that I showed you on the previous slide are melted between 350 and 465 degrees Fahrenheit. At this step, this is where different dyes may be used in the bags. Like when you think of Ziploc bags, you'll a lot of times think of the blue and pink zippers that they use on these. This is their brand's kind of identifying colors. Yeah, so from here, once these granules are melted, they do them in a kind of a steel cylinder, and they're slowly turned over top over bottom to mix while they are having the heat added to melt them. This ensures that there is a even distribution of the different polyethylene polymers and different chain, like the different variations, such as the linear low density and the linear polyethylene. The liquid plastic from here is, if you kind of envision a blow dryer blowing a thin cylinder of this liquid plastic. I guess maybe a bubble wand, like for children, is a better idea of this. When you blow air through this, it stretches this polyethylene into a cylinder that is hollow throughout the center. They can kind of elongate this cylinder, while it's cooling, they will come in with these different rollers to flatten the polyethylene film. It is flattened into the dimensions that they want, so it can be cut. And then once it is adequately cooled, they will use giant spindles to roll up the polyethylene into giant rolls that weigh approximately 350 pounds. These giant rolls of the polyethylene film are not yet processed. It's just basically flat polyethylene. It's almost as if you just made a sheet of polyethylene and then rolled it up, of course, starting with these polyethylene granules that I showed on the previous slide. So a lot of these bags will have their name brand or whatever put on them. This is done with a viscous alcohol-based paint that can be applied to bags via inking rollers. This alcohol paint is very viscous, and they keep it kind of turning in a vat at all times, which keeps it thin and from kind of coagulating. From here, it's much like your kind of standard ink printer to print out the ink over these bags as they kind of, as over the polyethylene as it's unrolled. So the actual making of the bag, if you think about an impulse sealer, something that uses heat to kind of seal together two objects, this is how the bags are made. So once you have two sheets of polyethylene that are the the shape and size that you're going to want for the bag, they use a heat sealer that's about 350 degrees Fahrenheit to come in and bind these edges together. So they'll do 3 of the 4 sides typically, which is going to leave you that one side open where the zipper is actually put on. Now these zippers are made beforehand using molds and heat sealing, a very, very similar process. The exact same compounds, and it's just, I mean, they may add dye, like I said, for the pink or the blue kind of zippers, but these zippers are simply put onto the bags the same way that the edges of the bags are sealed using heat. All in all, it's a fairly simple process. Once the polyethylene film has been formed, you just come in and add heat to the edges and it bonds everything together. Due to polyethylene's low melting point, this 356 down in the bottom left specifically refers to the heat in Fahrenheit, the temperature in Fahrenheit used to mold these bags together. The finished bags are stacked at the end of an assembly line, just one on top of the other. When you purchase a box of these, they often come folded end to end. I mean, there's typically like 100, 200 in a box, and they're just folded, kind of a sandwich fold. So it's nothing really complex here, and they have the boxing manufacturing could be a whole nother PowerPoint. They're just boxed depending on the shape and size of the bag. There's really not too much of variation too much of like a standard deviation in bag sizes. This is a fairly repeatable process, and the bags tend to come out the same size. From here, once they're put in the boxes, it's off to the stores for the consumers. So the processing effects on properties. The polyethylene chains, due to the covalent bonding, causes there to be a relatively high amount of elasticity within the bags. They are able to be, you can break these bags, however, it does require some amount of force. Polyethylene is fairly unreactive with many other compounds. There are certain solvents that will eat away at the bags, and of course, if you get them, due to their low melting point, if you heat them up too much, it will deform or damage the bag. Again, the bullet point below this high melting point is relative. I vaguely remember seeing a number that said 90 to 95 degrees Celsius for small amounts of time is fine with these bags, and it won't cause deformation or failure with the bags. These tight carbon-carbon bonds allow these bags to be airtight. There's not much that's going to be able to penetrate through these bags. If you've ever used one at home, you know that they'll hold water, they'll hold air. You can make a little air pillow out of them when you seal them off. They're relatively effective when it comes to containing or blocking out something from the inside. Um, Polyethylene is extremely cheap to produce, which is why it is commonly used for these bags, and it is also highly recyclable, which is of course good for the environment and um, good for the consumers. It allows us to buy the product at a cheaper cost. Similar products to these are going to be trash bags, grocery bags. If you've ever bought kind of like Morton rock salt or cat and dog food packaging that's got that plastic kind of a Ziploc bag texture to it, those are all made out of polyethylene. And any bag that's made primarily out of polyethylene, which the bullet points above this last one pretty much sum that up. So the textbook problems, there were no actual mathematical problems at the end of chapter 8 as far as I could find. So I went with 8.1, 8.13, 8.14, and 8.18, which you can see right here. So 8.1 asks what is a polymer, 8.13 is what is a plasticizer, 8.14, what are some additives used with polymers? 8.18, what is the chemical formula for ethylene, the monomer for polyethylene? So the solutions to these problems, 8.1, polymer is a compound consisting of repeating long chain molecules. These molecules are typically, well, they're not typically, they are monomers. They are kind of the basic building block of the polymer. They're the smallest repeating unit, which that N, if you think back to that parenthetical formula that I showed at the beginning, is the number of molecules in the chain. So a plasticizer is any kind of chemical that is added to a polymer to change certain physical properties. Like if you want to change the elasticity of it, you want it to be at a more of a rigid plastic, you are going to add what is called a plasticizer. It's fairly straightforward. However, the science behind it gets a little bit tricky with the different bonds and interactions at the chemical level. What are some additives used with polymers? Different lubricants, flame retardants, UV light absorbers. These can all be added into the bag, or excuse me, not into the bag, into the polyethylene while it is in liquid form to change certain properties of it. Like these can also alter physical properties. They're very similar to plasticizers. The chemical formula for ethylene is just C2H4. You can see the third slide again as a reference if you need to. It's fairly straightforward. It's one of the simpler monomers out there. And that about sums everything up. I have my references right here in case you'd like to backtrack on anything that I have posted in this video. Other than that, I am open for questions on my digication, and I appreciate you taking the time to watch this video. Thank you.